All right, here we begin chapter 3, and chapter 3 is all about chemical reactions and stoichiometry. So to get right down into the work, so reactions are described by equations. And specifically, we call these reaction equations. Okay, and just to give an example of the reaction equation responsible for the best and coolest molecule in the universe, looks like this. We have 2H2 plus O2 yields 2H2O. Okay, water, undeniably the coolest molecule in the universe. Now, by convention, we always refer to the items on the left side as reactants, and the items on the right side as products. Okay, later on, when we get into reactions that actually run both ways at the same time with equilibrium, we're still going to refer to the things on the left side as reactants and the things on the right side as products. Another concept about reactions is that they obey the law of conservation of mass. Okay, whatever we have on the left side has to equal what we have on the right side. So in our chemical reaction that we have written here, we have two times two hydrogen atoms on the left equals 2 times 2 hydrogen atoms on the right. Two times oxygen atoms on the left will equal 2 times oxygen atoms on the right. Okay, and we have 1 atom of oxygen on each side, just to make that clear. Okay, so the mass of 4 hydrogen atoms on the left has to equal the mass of 4 hydrogen atoms on the right. The mass of 2 oxygen atoms on the left has to equal to the mass of 2 oxygen atoms on the right. Now, when we are manipulating equations, this is an important fact. Never change subscripts on formulas. Okay, but we do change the coefficients in front. Okay, so looking at our equation that we have here, we're talking about these subscripts along the way. So I'm never going to alter those, okay? What I can play with are the coefficients in front. I can say how many hydrogen molecules that I have. I can say how many water molecules I have. In this case, the coefficient in front tells me that there are 2 molecules of H2. The lack of a coefficient means that there is 1 molecule. Okay, if it's a single molecule, we don't bother putting the 1. And then over here on the right, this shows me that I have 2 molecules of H2O. Okay, the 2 in front denotes how many of that item. But if I change the subscript to anything else, say for example, if I said just HO, that's a different molecule. Okay, it's no longer H2O if I change the subscripts. Okay, So when we're manipulating our equations, we never play with those subscripts, only the coefficients. Okay, so as a bit of an example question, okay, so if I write the question, how many atoms of magnesium, oxygen, and hydrogen are present, and what I give you is 3 MgOH2. Okay, that 3 means that I multiply everything by 3. Okay, so that means that I have 3 entire molecules of magnesium hydroxide. Right, so in this case, I will have 3 atoms of magnesium, 6 atoms of oxygen, and 6 atoms of hydrogen. Okay, this subscript 2 at the end tells me that there are 2 OH molecules. Okay, so everything inside that parentheses is beholden to that 2. So if I have 3 magnesium hydroxide molecules total, and each molecule has 2 oxygens and 2 hydrogens, that means that I end up with 6 of each. Our next topic is sort of related to this. So now that we have talked about understanding how many individual atoms we have in a molecule with a coefficient, let's talk about balancing entire equations. Right, so our first example is an example of what we'll refer to later on when we talk about reaction categories as a combustion reaction. So we'll have CH4 plus O2 yields CO2 and water. Okay, and this is unbalanced. Okay, so a handy tool, let me back up. So the point of balancing an equation is to cause an equation to obey the law of mass I can't talk. The law of mass conservation. Okay, I need to have the same number of each element on both sides. So a good tool for this is to make a list. On each side. Okay, so on the left side of my equation, I have a carbon, and I have 1 of them. I have hydrogen, and I have 4 of those. And I have oxygen, and I have 2 of those. Okay, I'm making a list of how many individual atoms I have on each side. On the right side, I have carbon, and there's 1 of those. I have hydrogen, and there are 2 of those. And on the right side here, I have oxygen with 3 of those. Okay, so strategies. Right, so one of our strategies is to start with elements in the elements in the fewest compounds. Okay, in this case, things are pretty well distributed, so that strategy is not super handy here. Our other strategy is to leave single elements for last. Okay, in this case, we're going to be talking about the oxygen. The oxygen's all by itself on the left-hand side. So we're going to balance that one last. Okay, so looking at what we have here, in order to make things equal on both sides, we are going to add coefficients in front of things. Again, I'm not going to play with any of these coefficients, or the subscripts. Okay, all the subscripts must remain the same. So I will never touch those. But I can put coefficients in front of compounds or elements in order to make things balance. Okay, so just to talk through this, on the left side I have 1 carbon, on the right side I have 1 carbon. So they're balanced. The hydrogen, on the left I have 4, on the right I have 2. I need 4 on both sides, or at least they need to be equal. So an easy thing for me to do is to put a 2 in front of the water on the right-hand side. Okay, so when I do that, that causes my hydrogen now to be 4 of them, and it changes my number of oxygens. So now I have 2 oxygens in the carbon dioxide, and now 2 oxygens in the water, with a total of 4. Okay, so at this point I have 1 carbon on each side, 4 hydrogens on each side. Now let's look at the oxygens. I have 2 on the left and 4 on the right. So if I put a 2 in front of the O2 on the left, that now makes 4 oxygens on the left and 4 oxygens on the right, and we're balanced. Okay, I need to have the same number of each element on both sides. So now let's try a trickier one. C8H18, also known as octane, plus O2, again yields carbon dioxide and water. Now we're going to use a bit of a trick here, and we're going to employ the help of fractions. Okay, when we get there. So let's talk through it. Nice little strategy is to make a list of what I have on both sides. So I have carbon, and there are 8 of those. I have hydrogen, and there are 18 of those. And oxygens, I have 2. On the right, I currently have 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so the easiest one to start with is carbon. So I have 8 on the left, 1 on the right. So if I put, and let me change colors here. If I put an 8 in front of the carbon dioxide, that now gives me 8 carbons on both sides, and it gives me 17 oxygens on the right. Okay, so let's look at the hydrogens next. 18 on the left, 2 on the right. So if I put a 9 in front of the H2O, that now gives me 18. And let's say 16 plus 9 means now I have 25 oxygens on the right and 2 on the left. Now here's the trick. I can't just put a 25 in front of the O2, because that would give me 50 oxygens on the left and 25 on the right. But if I take and put this as 25 over 2, then that means that I now have 25 oxygens. But the problem is I can't leave it as a fraction. Right? So what I'm going to do to get rid of that fraction is multiply the whole thing by 2. Okay, so if I multiply the entire equation by 2, then what I do is I end up with 2C8H18 plus 25O2 yields 16 CO2 plus 18 H2O. Okay, so you can sort of plug and chug, try different things, mess around with coefficients until everything balances out. The fraction method gives you a sort of quick and dirty way to get the correct number of oxygens on both sides, and then you can eliminate the fraction by multiplying the entire thing by the denominator. Okay, I'm going to go ahead and stop this video right here. We'll come back with our next video talking about states of matter in chemical equations.